You good? I'm very excited today to show you how your browser can prove this one specific lemma in this case. So this is the work I'm doing with Tim Gowers and Mateo Jamlik in the computer lab. And the idea essentially is there are already lots of automated theorem provers out there, so Koch, Agda, and Isabel are the big ones. And they're all really good at what they do, but they don't really, they're more interested in verifying that problems, that the proof is true or something like that. So if you actually want to understand how this thing is arriving at certain conclusions, they're not as good. So the aim of this project is to work on a system with, or demonstrate that it's possible to make a system which kind of reasons similar to how a human might reason, to both convince more convincing write-ups and also to kind of give a kind of interactive interface which a user could step in and start investigating different lines of reasoning, things like that. So I hope you can see this. I'm going to get a bit bigger. So the idea is, so we're going to have three different things. We're going to have the write-up, the proof state, and the proof expression. And all of this is happening on the client in the browser. So there's no, this isn't a slideshow. This is JavaScript's actually calculating this as we go along. So you'll see that we have this diagram where we have some box, and then we have a vertical line and a horizontal line. So everything that's under the line is the thing we want. Everything above the line is what we have. Okay, so I'm not going to go into the terminology too much or exactly the specifics of how it works. If something has a dot next to it, it means this is what we are trying to show. We're trying to find something. So I'm not going to talk too much about proof expression, but just about write-up and proof state. So the first thing we're going to do is run some simple heuristics on the proof state, and then that will slowly change the proof state and along the way generate a write-up. So yeah, so onwards show. So that's the first thing it does. So you can see how it's saying let x be a metric space. That's our first step. X and y be metric spaces. X, y, z be metric spaces. F is a function, g is a function. Now we suppose f is continuous and that g is continuous. And this is a bit clearer now, perhaps. Let me zoom in. So you can see everything above the line is what we have, and everything below the line is what we want. So we want to prove that G circle F is continuous from all of the facts above. Below, this thing that's generated here is a formal representation of the proof, so which we can actually feed into these established tools just to completely verify everything's true, because the computer scientists care about that kind of thing. But we're going to be more interested in the write-up, which is a which is generated directly from the moves that we perform on the proof. So, okay, let's continue. So we're going to start expanding definitions. So, yeah, keep an eye on write-up. Keep an eye on what the write-up's doing. So let epsilon greater than 0. Good so far. Next. And you can see here it's starting to expand out definitions into logical forms. So the hope is eventually this will also be a write-up, so it will say something like for all epsilon, etc., etc. Okay. So now this is kind of the innovation, is that the we must choose is done with something called meta variables, and we have these strange representations where we want to find delta dot and also T12, which is the thing we're trying to prove. So we need to choose delta later to get this to work, which is kind of how humans work, right? You don't immediately go in and know what the data is, what the delta is. Okay, so we're going to continue. There's just some rewriting going on downstairs, nothing interesting. Okay, and then so this is the next line, since G is continuous, seems sensible. Since F is continuous, same step, and then we are done by choosing delta to be theta. So all of that is done automatically. Every step of that is automated. There's no smoke and mirrors there. So I guess to finish off, note that there is also some interactive elements as well. So I can do something like swap over y and x, or I can use the triangle rule, and then it generates a load of different targets that I have to meet and things like that. So there are other ways of proving things, but I'm just showing you the automatic thing at the moment. So yeah, I think that's pretty much all I wanted to say. So yeah, come and meet me and I'll show you some other examples as well. Thank you very much.
Thank you, Edward. So